Let's look at a 16b for SL students, 19b for HL students. So the topic of this lesson is increasing and decreasing functions. So in this lesson, we need to apply the first derivative to determine the increasing and the decreasing intervals for functions. Let's review intervals. The increasing or decreasing intervals are the subsets of a function's domain. So when we talk about the increasing, decreasing intervals, we should base on the domain of the function. We have two different forms to express the increasing, decreasing intervals. The algebraic form. Algebraic form means we use the inequalities to represent the increasing or decreasing intervals. Or geometric form, so we use the number line with the open dot or the closed dot to show what numbers we can take for the increasing or decreasing intervals. HL students also need to know how to use the set notation or interval notation to represent increasing or decreasing intervals. So know what x is greater than or equal to 2 mean on the number line. So that means all the numbers greater than or equal to 2. So 2 should be a closed dot on the number line because 2 is included in this interval. When x is greater than 2, not equal to 2, so we use the open circle, open dot on number 2 and show all the numbers are greater than 2 only. So x is less than or equal to 2. There's an equal sign here. So all the numbers less than. So you show the numbers on the left side of 4. And this 4 should be closed circle. X is less than 4. All the numbers on the left side of 4 and open circle on number 4. X is between 2 and 4 inclusive. So all the numbers are between 2 and 4. And both of the 2 and 4 have the equal signs. So 2 and 4 are the closed dots on the number line. X is greater than or equal to 2 but less than 4, no equal sign on 4. So all the numbers can be between 2 and 4. 2 is included. 4 is not included. Therefore 2 is the closed dot. 4 is the open circle or open dot. Section 2, let's look at the definitions of increasing and decreasing for functions. Suppose S is an interval in the domain of f of x. So f of x is defined for all x in this interval S. If f of x is increasing on this interval S, if and only if f of a is less than or equal to f of b for all a, b values on this interval such that a is less than b. What does that one mean? So when f of x is increasing on one subinterval, so a is less than b, that means you look at the graph from the left side to the right side in the coordinate system. When x is getting larger and larger, your y value is getting larger and larger. This function is increasing. F of x is decreasing on the subinterval S, if and only if f of a is greater than or equal to f of b for a and b belong to the subinterval S such that a is less than b. So this one means when f of x is decreasing on a subinterval of the domain, when x is getting larger and larger, your y value is getting smaller and smaller. So in this case, this interval is the decreasing interval. Let's look at this example, y equals x squared. This parabola has both increasing and decreasing intervals. What is the increasing interval? So let's look at when x is getting larger and larger, y is getting larger and larger. So that should be the right side of the parabola. So the increasing interval is x is greater than 0. Or you can write as x is greater than or equal to 0. You can include the 0 or do not include the 0. It's up to you. Because the 0, this point, really doesn't affect the increasing interval. One point does not affect one interval. Decreasing interval. Decreasing interval, let's look at this part. When x is getting larger and larger, y value is getting less and less. So decreasing interval is x is less than 0 or x is less than or equal to 0. The same to explain the 0. X can have 0 included. Or you don't have to include 0 for x because one point doesn't affect the decreasing interval either. But right now we need to relate the increasing interval and the decreasing interval to the first derivative. Let's look at the increasing interval, which is this one. Look at if I draw the tangent to the curve at any point on this increasing interval, this tangent should have positive slope. So this tangent f prime x is greater than 0. Or you can say f prime x is greater than or equal to 0. The f prime x is the same as y prime, okay? So y prime is greater than 0 or y prime is greater than or equal to 0. Decreasing interval. This is the decreasing interval. If I draw a tangent to the curve at any point on this interval, look at the red one. This slope is negative. Or you can say f prime x equals y prime is less than or equal to 0. When y prime equals 0, so you have the horizontal tangent line. On this parabola, there's only one point where you can draw the horizontal tangent line. It's at x equals 0. So once you draw this tangent line at x equals 0, you know x equals 0 can be included in the increasing interval or excluded in the increasing interval. The same can be applied to decreasing interval. So this reason, I can include a 0 for the first derivative or do not include a 0 for the first derivative. Let's summarize what we learned from section 3 again. So for increasing, that means the gradient of the tangent, which is the first derivative of this function, should be greater than or equal to 0. When you have f prime x just greater than 0, that's called a strict increasing. For decreasing, so when you have a decreasing interval for a function, the gradient of the tangent line to the curve on this interval should have negative slope. So that means the first derivative is less than or equal to 0. When you have the first derivative less than 0 only, this is called strictly decreasing. The word strictly is really not required for this course, for both HR and SL. But it is useful for understanding. So when we talk about increasing or decreasing intervals in both SL and HR courses, we only need to either use this one or this one. This one or this one for decreasing. You don't have to really differentiate. This is the increasing, this one is the strictly increasing. We don't have a differentiation on increasing and strictly increasing. You can use any way to represent the increasing, any way to represent the decreasing interval. So monotone increasing means the entire function is increasing for all x on the real number system. F of x is increasing for all x on the real number system. You don't have a decreasing trend for this function on the real number system. This is called monotone increasing. Likewise, monotone decreasing means f of x is entirely decreasing for all x when x is on the real number system. Example 1, find the intervals where f of x is increasing in A. B, decreasing. So let's observe the graph. So increasing part should be from this minimum point to that maximum point. Local minimum, local maximum. That's what we will call later on. Okay. This point to that point. X is getting larger and larger, Y is getting larger and larger. This is increasing interval. Like what we just introduced in section 3 and section 4, you guys know that you can either represent the increasing interval as 1 is less than or equal to X is less than or equal to 5, or you just say 1 is less than X, less than 5. You don't have to include the equal sign for this inequality on both of the boundary points. Decreasing. Let's look at a decreasing interval on the graph. When the X is getting larger and larger, this Y is getting less and less, decreasing. When X is getting larger and larger, Y is getting less and less, decreasing. So decreasing interval can be written as X is less than or equal to 1, or you can say X is less than 1 only. The other decreasing interval is, the other one is X is greater than or equal to 5, or X is greater than 5. Please note that when you represent the increasing interval and the decreasing interval, you only use the X values rather than the Y values. So you always use the subinterval on the domain of the function rather than the range. So always talk about X for the increasing or decreasing intervals. Let's look at example 2. Find the intervals where the following functions are increasing or decreasing. This time, the graph is not given. Of course, you can graph it to observe the increasing and the decreasing intervals. You're familiar with y equals negative x squared already. This graph is in a parabola opening downward. So this is the increasing interval. This is the decreasing interval. But this time we want you apply the first derivative to determine the increasing or decreasing intervals algebraically. So let's find its first derivative. Y prime. Y prime equals negative x. When this negative 2x y prime is greater than 0 or greater than or equal to 0, you should have increasing interval. When this negative x is less than or equal to 0, you should have decreasing interval. Anyways, negative 2x is greater than 0, negative 2x is less than 0. Usually later on we just say we use the negative 2x equals 0 as the splitting point. X equals 0 is the splitting point on the number line. When x is on the left side, you just look at when x is less than 0, right? You just look at if I pick up an x value and plug into y prime, should the y prime be positive or negative? So let's take any value, negative 1, negative 2, plug in. Negative 2 times negative 2, positive 4. So this one will produce y prime greater than 0. Pick up any value from the right side of x equals 0. So this is also x is greater than 0 interval. So pick up any value 1 or 2, plug in. The y prime will be negative. So from this number line, with the positive first derivative and negative first derivative, I can know the increasing interval is x is less than 0. Because on this interval, y prime is positive. The decreasing interval is x is greater than 0 because on this interval, y prime is less than 0. And you will find that these two increasing, decreasing intervals can be found through these two linear inequalities as well. So when negative 2x is greater than 0, x is less than 0. Because you divide both sides by negative 2, you need to reverse the sign. And this one means x is greater than 0. So increasing interval, decreasing interval. Of course, you also can represent the increasing interval as x is less than or equal to 0. You can also represent the decreasing interval as x is greater than or equal to 0. You can include the 0 in increasing or decreasing interval. Let's use the algebraic way to determine the increasing or decreasing interval for the second function in B without graphing it. Some of the SL students may not be familiar with this function, but HL students should know this function. This function, y equals negative x cubed, should look like this one. Y equals negative x cubed. You will see this entire function is decreasing on its domain. X is all real numbers. So this is a monotone decreasing. But let's use the algebraic way to show it's really increasing on the real number system. So let's find y prime. Y prime should be negative 3x squared. Let's make this one equal to 0. X equals 0. On the number line, this x equals 0 is the splitting point. So split into less than 0, greater than 0. And you should know this function has the domain of real numbers. From negative infinity, positive infinity with 0, you should produce two intervals. X is less than 0, x is greater than 0. And this domain also is all real numbers. That's the reason why I can have x is less than 0, x is greater than 0 on the domain. So when x is less than 0, you pick up any x value to determine the positive sign or negative sign of the first derivative. So for example, x equals negative 1. Let's plug in. Negative 1 bracket squared is always positive times negative 3. Negative. So pick up any value from this interval, x is greater than 0 interval, 1. 1 squared, 1 times negative 3. Y prime is also negative. And at this point, y prime is equal to 0. You will see when x is less than 0, y prime is less than 0, decreasing. When x is greater than 0, y prime is less than 0. So y is decreasing. So this function only has a decreasing interval. And the decreasing interval can be written as x can be all real numbers. Because equals 0 doesn't really affect the decreasing or increasing interval. You can include it. When you include it, you can just write out the decreasing interval as all real numbers. So this information is consistent with what we can see from the graph. So this graph is monotone, decreasing. Let's find the increasing or decreasing interval for this cubic function. If you want to graph this one, I think this is challenging without using a graphing calculator. It's harder even for me to graph this function without using the calculus knowledge or the graphing calculator, right? So we don't graph it. We need to discuss its interval for increasing or decreasing, okay? So let's find its first derivative. The first derivative should be negative 3x squared plus 6x. Let's say y prime equals 0. Find the 0 derivative points. So it should be negative 3x times x minus 2 equals 0. So x can be 0, x can be 2. So when you want to plot those 2 points on the number line, so x equals 0, x equals 2, these 2 points will make y prime equals 0. But these 2 points chunk the real number system into 3 intervals. Why did I say the real number system? Because this function should have the real number system as its domain. So the domain should be x can be all real numbers. From negative infinity to positive infinity. So 0 and 2 can chunk negative infinity to positive infinity to 3 intervals. This interval should be x is less than 0. This interval is x is between 0 and 2. And this interval is x is greater than 2. So then you pick up a value from each interval to test the sign of y prime. So let's pick up x equals -1. Then sub into this factored form. It's easier for you to determine the sign with the factored form for y prime. So x equals -1, -3 times -1, positive. -1 minus 2, negative. Positive times negative, this y prime is negative. Between 0 and 2, let's pick up any x value. For example, 1. Let's test the sign of y prime. So -3 times 1, negative. 1 minus 2, negative, negative, negative become positive. Do the same thing on this interval. So let's pick up x equals 3. -3 times 3, negative. 3 minus 2, positive. Negative times positive is negative. So I can know increasing interval should be 0 is less than x, less than 2. X is between 0 and 2. Of course, you also can represent this one as x is between 0 and 2, inclusive as the increasing interval. Decreasing interval, so y prime is less than 0. So x is less than 0 or x is greater than 2. If you want to include the equal sign, feel free to do so. You also can include the equal sign for these two inequalities to show the decreasing interval. So after I got to the increasing, decreasing interval, I can sketch the graph roughly. So between 0 and 2, you should have increasing. And you also can find the y-intercept. So when x equals 0, the y-intercept is 5. So look at between 0 and 2 should have increasing. Then decreasing when x is greater than 2. When x is less than or equal to 0 or less than 0, it's decreasing as well. So this cubic polynomial should look like this one. If you don't believe this sketch, you can check this rough graph on the graphing calculator. The trends for increasing, decreasing must be accurate. Some of you guys may ask, how did you know you should increase to this much high to get to the local maximum here? Of course, for this point, we need more calculus knowledge to help us later on. So we will try to finish all the knowledge piece by piece and put them together to finish the entire graph based on the first derivative knowledge later on. Let's apply the same process to determine the increasing or decreasing interval for this quartic function in D. And then sketch its rough trend based on the increasing and the decreasing intervals. So let's find y prime first. Should be 12x cubed minus 24x squared. Let this y prime be 0. And also remember, you need to look for its domain. The domain of this quartic polynomial function should be x can be all real numbers from negative infinity to positive infinity. So let's solve the 0 points of this y prime. We can use the factoring to solve this equation. So one x equals 0, the other x equals 2. On the number line, let's label these 2 points. So one is x equals 0. At this moment, y prime is 0. X equals 2, also y prime equals 0. And these 2 points can chunk negative infinity to positive infinity into 3 intervals again. X is less than 0, x is between 0 and 2. X is greater than 2. Let's determine the sign of the y prime in each interval. Y prime here, pick up any x value and sub into this factored form of the y prime to test the sign of y prime. So x equals -1, positive times negative. So this y prime is negative. Pick up any value between 0 and 2. Let's say 1. Plug in positive times negative. Y prime is also negative. Let's pick up any value from this interval. X is greater than 2. So let's say 3. Positive times positive. 3 minus 2 positive. Y prime is positive. So you will see the increasing interval is x is greater than 2 or x is greater than or equal to 2, because on this interval y prime is greater than 0. Decreasing interval should be x is less than 0 or x is between 0 and 2. If you include this x equals 0, anyways, it should be x is less than 2 or x is less than or equal to 2. That's decreasing interval. So 2, you will have increasing on the right side of 2, decreasing on the left side of 2. And if you really want to sketch this graph roughly, we need to find the y-intercept. Let's say x equals 0, so y equals 2. So 2, this y equals 2 is the y-intercept. So increasing, decreasing. But how low can you go here? And why there is such a kind of twist at the y-intercept point? Of course, for these two properties, we need more calculus knowledge in order to help us understand why we can have those features on the graph later on. But the trend must be correct. So x is less than 2, decreasing. X is greater than 2, increasing. You can use your graphing calculator to check the trends right now. Example 3. Consider f of x is negative x squared plus 4x minus 7 divided by x minus 1. This function is more complex than all the functions in example 2. This is a rational function. Show that f prime x is this one and draw its sign diagram. Hence, find the intervals where y equals f of x is increasing or decreasing. So let's look for its first derivative based on its instruction. So this is a quotient, so we need to apply the quotient rule. Let u be negative x squared plus 4x minus 7. V be x minus 1. So u prime should be negative 2x plus 4. V prime should be 1. F prime x should be u prime v, low d high, minus high d low, uv prime. So it's negative 2x plus 4 times x minus 1 minus negative x squared plus 4x minus 7 times 1 divided by v squared to go. So right now we only need to simplify the numerator. Let's keep the denominator the same. So expand the numerator, negative 2x squared plus 6x minus 4, and combine the like terms. So expand the brackets, combine the like terms. That's what we can get from this one times this one. Then the second one should be plus x squared minus 4x plus 7. So f prime x is x minus 1 squared. Then the top should be negative x squared plus 2x plus 3 if we combine the like terms further. Let's look at this numerator in comparison with this numerator. This one reminds me I need to factor the top. So let's factor the top. So x minus 1 squared, take out the negative sign, x squared minus 2x minus 3. Let's factor the trinomial, negative x plus 1 times x minus 3. So this is the first derivative. Let the first derivative be 0. So we can have the numerator equals 0. So x equals negative 1, x equals 3. Denominator cannot be 0. Negative 1, 3. And then remember, for f prime x, there is a denominator. So x equals 1 should be the undefined value for y prime. So this y prime should be 0. This y prime is 0. So right now we need to look at how many intervals we have in order to discuss the increasing decreasing interval. This interval is x is less than negative 1. This interval should be between negative 1 and 1. This interval should be between 1 and 3. This interval is greater than 3. Why can we have 4 intervals? Because you look at the domain of the original rational function. The domain x can be all real numbers except 1 in the denominator. So 1 is not only the undefined value for y prime, but also the undefined value for the original function. This is the reason why x cannot be 1. So you need to exclude the 1 from your increasing and decreasing intervals. Then from negative infinity to positive infinity, these two 0 points and the undefined value x equals 1 can chunk the whole number line into 4 intervals. So x is less than negative 1, negative 1 to 1, 1 to 3, x is greater than 3. Next, we need to pick up a particular x value from each interval to test the sign of f prime x. So when x is less than negative 1, we can pick up negative 2, for example. So when x is negative 2, let's plug into this factored form in the numerator and the denominator. So x equals negative 2, negative 2 plus 1 negative, negative 2 minus 3 negative. Negative times negative is still negative. The bottom must be positive, so the top is negative. So on this interval, y prime should be less than 0. Between negative 1 and 1, let's pick up x equals 0. Let's plug in. Negative 0 plus 1, negative 0 minus 3, negative, negative, negative become positive. Bottom is positive. So this y prime is greater than 0. So from 1 to 3, let's pick up x equals 2. Let's test the sign of y prime. So this 2 should be positive, negative, negative. It's still positive for the numerator. So the bottom is positive. So on this interval, y prime must be greater than 0. So when x is greater than 3, let's pick up a 4. So 4. So positive, positive, negative. So y prime should be negative. Therefore, the increasing intervals are negative 1 to 1 and 1 to 3 for x. Because on both of the intervals, y prime is greater than 0. Do not put an equal sign on 1. You can put an equal sign on negative 1 and 3, but you cannot put an equal sign on 1 because the original function has x equal to 1 as an undefined value. Decreasing intervals. There are 2. So one is x is less than negative 1. The other one is x is greater than 3. You can include the equal sign for each interval. This function is more complex. We don't graph it because we don't have enough knowledge to graph the properties on the graph in details. So we only discuss the trends of this rational function. This is the end of this lesson.